quantity of charge through a conductor is small as Q equals 4.00 coulombs over seconds to the 4 T4 to the 4 minus 1.00 coulombs over second T plus 6.00 microcoulombs. So this is an equation of the charge as a function of time. This is an equation that models the charge as a function of time. They say, what is the current? What is the current? At time t equals 3.00 seconds. Now, do you remember the rule of derivative? Who did calculus already here? You did calculus, Sharon. Who else did calculus? Calculus. Who else? You didn't take calculus? You're taking it right now? Okay. So we know that if we have a function x to the n, or an expression, x to the n, the derivative, the first derivative of x to the n, sorry, let me just rewrite this in a different way. Yeah. With respect to the variable x, it would be n times x to the power of n minus 1. This is the first derivative of x to the n, right? It's n times x to the power of n minus 1. So why we have to remember this? Because now Q, the charge at the time, you want to find the current. The current is the Q of t dt, right? The current is dq dt, but Q is a function of t, so it's dq of t dt. So you say derivative of that without the coulombs over second to the fourth, just eliminating, these units. The function Q of t is 4.00 t to the fourth minus 1.00 t plus 6.00. I am not gonna put in the units at all here, dt. So what happens if I apply now the rule of differentiation? This half exponent 1, I will multiply by this exponent 1, I will multiply by this exponent 4, but I will be subtracting 1 from the exponents, right? So this would be, when you find the derivative, 4.00 times 4 t to the 4 minus 1 minus 1.00 times to the 4 minus 1 minus 1.00 times 1 e to the 1 minus 1, right? Plus this one have a t to the 0. That's why the constant, the derivative of a constant is always 0, right? So at the end, this is just 0 because the derivative of a constant is always 0. So this would be 16.00 t to the third minus 1.00, t to the 1 minus 1 is t to the 0, t to the 0 is 1. So you get that I of t is 16.00, t to the third minus 1. So this is the equation of the current as a function of the time after finding the derivative. After finding the derivative of the function q, the function charge. So now, if they want to find the current at time 3 seconds, say I of 3.00 seconds would be 16.00 times 3.00 seconds to the third minus 1.00. And I of 3.00 seconds, or at t equals 3.00 seconds, we calculated 432 here minus 1.00, which is going to be, in this case, 431 milliamperes, or 0.431 amperes, of 0.431 amperes.